1 minute.
So,
Right.
Simon,
Can you guys see the screen?
Yeah, sorry, Steve. Did you get the list of the participants? I think Hugh sent it through.
Yes, I did get a list of, yeah.
Okay, cool.
Right. So most of it is just going to be me walking through the configuration and stuff like that. But I'm going to just give a few words for DMP so that at least we are on the same page when we go through the configuration.
Sure.
All right. So this is an application example of what you'll be looking at with the DNPSNET module. So what you're going to be able to do is perform DNP communications over Ethernet using our card. All right. So at one side you could have a SCADA, you could have a bunch of IEDs all communicating with our card, but you're going to need your SCADA to be the client to communicate with the DMPS card, because our DNPSNET card is only going to be operating as a DMP slave or a DMP server. Right. So some features of a card, of course, you have a DMP over Ethernet. It incorporates timestamp communication and easy communication with IEDs. Then when we look at the DMP protocol, something that we're going to talk about in more detail when we do the configuration. So when you're communicating with a device on DMP, what you're going to have are communication points. So you're going to have points being written from one side to the other, be it from the server to the client or from the client to the server. Right. So when we talk about data communication for DMP, the data is going to be classified not just by a specific point number, which is an identifier for that point, but it's also going to be classified by a variation as well as an object type. So for example, a binary object would have a specific object type, for example, object 1 for binary input, and a specific variation to say the nature of the point as it is communicating. So when you're looking at point addressing in DMP, you're going to be looking at 3 things. You're going to be looking at the point number, you're going to be looking at the object or the object type, and then you're going to be looking at the object variation. So all those 3 things have to be specified as a client or as a server in order to get communication. Now, another form of communication that you have with DMP is you're also going to have class communication. So you can group your data into a specific class, and then that class is going to be pulled by the client as a whole. So you can have class data transfer from one side to the other side, and it's always from the server to the client. So in the server, you group a class of data, and that data can be sent from the server to the client. Now, what you can't have is a class, what we call a class write, where you have the client forcing information for an entire class. So class commands are only going to be essentially data transfer from the server to the client device. We're going to talk more in detail when we go through the configuration, and then you guys are actually seeing what I'm talking about. Then the next part of the communication is going to be communication between our card and the controller itself. Right. So for our card, right, you're going to have just 1 minute. All right, so for our card, you're going to have you're going to have a backplane communication between our DMP INREX card and the Logix processor. So what you're going to have is a sort of separation of the INREX card. And then you have communication on both sides. So you have communication on the DMP side, as well as communication on the backplane side. So when we walk through the configuration, we're going to configure communication side by side. And then we're going to troubleshoot and diagnose that communication as well, side by side, so that you see exactly how the data is going to be flowing from the DMP into the module, and how it's going to be going out of the index module and going to your processor and your processor tags. So the steps that we're going to follow for this demonstration, we're going to download the sample ACD file from Process Technology website. We're going to create a module in the PCB, and then we're going to configure it. We're going to change the file to match the PCB configuration. We're going to download the ACD file to the PLC, then we'll download the PCB configuration file to the module. So I'm going to walk you guys through the whole thing step by step, starting with downloading the ACD file itself. So that. All right, can you guys see the Chrome screen?
Yeah, we can see where you are. We're just waiting for you to browse to the site to download.
All right, that's okay. If you guys have any questions, just send them in the chat, and then I'll either cover them as we go, or we'll talk about them right at the end. Right, so if any questions come up, just send them in a message in the chat.
Yep.
So all right, continuing from the Process website, if you go to our products, Roku Index, Compact Logics, DNPSNET. So under downloads, what you're going to find is the user manual is going to be useful for when you're setting up the module, because it will give you all the information that you need for the setup. And well, of course, you have support, so you can email us if you have any questions. What we are going to be concerned with are two things. You have the add-on profile, which is an installable program that you install and then you need to integrate with your Logix Studio 5000. And then you have the sample ladder or the sample ACD file. Right? So if you click on that one, it's going to actually download an ACD file that we're going to open and work with to configure. Now, we also give you a sample configuration file that is matched to the sample ACD file that we give you. Right? But I don't want to have to start from already pre-made configuration. I want to start one from fresh. Right? So the first part, if we look at our list, is download the ACD file, and we've just done that. So now we want to go on to the next part, which is going to be configuring the module in PCB. Right? So PCB is our process configuration software. You can, if you don't have it, again, you can download it from our website. It's free to download. In the process, you have our PCB, which is our process configuration builder. So process configuration builder is the starting point for all things process Index. Right? So all the Index configurations are going to be done out of process configuration builder. And it looks something like this. Right? So we want to create a new file. And then what the new file is going to do is it's going to ask you to create a type of module. We want to create an MVI69 DNPSNET module. Okay, and then it will create something like this. Right. Now let's walk through the configuration step by step. The first part of the configuration that you're going to have is the backplane configuration. Now, if you remember, I mentioned that we are going to configure the module in two halves. So you have the first half that is communicating with the Logix controller itself, which is the backplane configuration. And then you have the second half, which is communicating with the DNPNet side, which is the DNPSNET slave side.
Excuse me, Simon.
So basically, yeah.
Simon, Steve.
Yes.
I've got a widescreen laptop on a projector on the wall that doesn't quite show the whole of the ProSoft configuration builder. Can you restore it down and just manually resize it so we can see everything?
Okay.
That's better.
Right,
just operate in that mode, please. Yeah.
All right, like that.
Yeah, that's good.
All right, so I was saying you're going to have two sides to your configuration. You have a backplane configuration, which communicates with your PLC, and your DNPNet side configuration, which communicates with your DNP device. Right. So we'll start with the backplane configuration. Under backplane configuration, you're going to have the following configurable registers. Right. So how our module operates, just so I can demonstrate to you guys. So let's go to paint. Right. So our module is going to operate as move those grid lines. As a stand-in device with an internal address that starts from 0 to 3,999. So you're going to have a 4,000 integer register internal address, right? And this is going to be represented by our MVI69 card. So what you're going to have in your communication, on one side, you're going to have the PLC. And then on the other side, you're going to have your DNP device. So when you look at our PCB configuration, let me just open that. The module part, the backplane configuration, is going to be configuring the communication between our module and the PLC side. So you're going to have stuff like read start, read count, write start, write count, block transfer size. So what that means is the following, right? So what you're going to have is communication going back and forth in this side. So you have communication that goes that way. And then you're going to have communication that goes that way. So for that communication, this one is going to be what we call a write event, because the processor or the PLC is writing into the internal database of the MVI69 card. And then from this side, what you're going to have is a read event, because essentially the PLC is going to be reading out of the Modbus card. So when you get this part of the configuration, what you're going to be setting are certain locations where you say this part of the configuration is going to be in the read part of the data. And that part of the configuration is going to be in the write part of the data. Right. So you have something like, with the current configuration, you're going to have part of it that goes from 0 and stretches up to 99, which is going to be a count of 100 registers. And then these are going to go this side as read data. In the same way, you're also going to have a range of data that is going to store information that comes from the PLC, which is going to be your write data. And in the current configuration, this is going to run from 100 to 199. So you have a count of 100. That's the configuration that we have here. So if you look at this configuration, it says module read start 0. So that's going to be the read start part. And then it says read count 100. So you're going to have 100 of these registers being sent from the MVI card to the PLC. In the same way, for the write start, just write from 100, and then you're going to have 100 of those. So you're going to have from address 100 of the internal database to address 99 going to the PLC, into our MVI card from the PLC. Right. So the idea with communication using the card is that you're going to need to have a flow of communication from one side to the other. That means you're also going to need this guy writing to that same location, and this guy reading from that location. That way, you have an actual flow of information from one side to the other side, and an actual flow of information back. Now, you wouldn't be able to communicate, for example, if these were going to be reversed. If we're going to reverse these, you're going to have a situation where this one is reading from there, and this one is writing there, and this one is writing there. These are going to override each other, and no one is going to be able to communicate there because you have both of them just reading zeros out of the MVI card. Right. So that is the current problem that you're going to have with this initial setup. Something that I'm going to talk about a little bit later, but let's go to the other part of the configuration. You have block size transfer. Now, what this block size transfer means is that this information that we've set up is going to be divided into small blocks. The blocks are going to be 60 in size, right? So there'll be 60 integers there, and then there'll be another 60 integers there, another 60 integers there, and so on and so on. So the information is going to be sent to the PLC in blocks of 60. Right? So you're going to have this 60 go, this 60 plus a bunch of padding going this side. You have another 60 for this part, and another 60 for the remainder, and a bunch of padding coming from this side. Right? So you're basically going to have block transfer in the size of 60. So if you have 600 integers of data that you're pulling, you're going to have 10 blocks going back and forth between the PLC and the MVI69 card. That's basically what that means. Then you have the error flag. Sorry?
Sorry, so just that figure of 60, is that just a generic figure? I mean, when you're doing, say, the blocks of 100, would you be writing 100 in there, or is that like too large a parcel of data, or?
Yes, for control logics, right, you can configure it between, you can either put something in the range of 60, something in the range of 120, and something in the range of 180. Right? We just use 60 as the default because 60 works fine. If you wanted to pull faster data, you could use a higher value, like 120. But then it's all going to depend on your RPI, because if you have a fast RPI, you won't get much difference if you increase the data size.
Yeah. All right, thanks for that.
All right. So, failure flag counter is just a counter that counts the number of failures that you're going to have on your backplane. You have an error offset, which is going to be a place in the internal database where you store your error. Right? So what you'll have in the internal database, as I showed in Paint, you're going to have access to a database from 0 to 4,000, from 0 to 3,099. In reality, our database goes a lot further than that, but now you don't have access to this. This is only for diagnostic information, so you won't be able to see the tags in there. Right? But then we have a lot of people who would want their error tags to go from the card to the PLC. That way, the PLC can see in real time whether there is an error on the communication of the card. So we allow for that facility in our configuration where you can set an error offset and change this value to somewhere within the read part that you have. Then you have an initialize output value, which is basically saying when we start the module, what is the value that we want on the output tags. So you could initialize it to a specific value like 0, or you could just disable output data initialization completely, which is what we've done here. So the next part of the configuration, this is the configuration with the PLC. The next part of the configuration is going to be the configuration with the DMP side, right, which is this side. So Let's undo a bunch of stuff that we've done. All right. So you're going to have communication between the DNPNet client and the card working as a DNP server. All right. Now, in this part of the communication, the way that data is going to be stored for DNP is going to be sequentially, depending on how the module is configured. All right. So you're going to have this configuration that we have set up here, where you have binary inputs, analog inputs, float inputs, counters, binary outputs, analog outputs, float outputs. Now, these are going to be stored in the database in a sequential manner. So immediately after the binary inputs, you're going to have the analog inputs. Immediately after the analog inputs, you're going to have the floating point inputs. Right. So you're going to have a case, for example, here you have binary inputs 10. Right? That means the first 10 registers here are going to be our binary inputs. All right. Now for our implementation on DNP, when we store our binary inputs, we store them as integers. So they'll carry integer values. They'll carry the integer format. And then if you send one binary high, it's going to be stored as a 1 in the entire 16 bits. Right. That's why if we say you're going to have 10 binary inputs here, you're actually going to occupy 10 integer registers. Right. So the next one after that is going to be analog inputs. So we're going to need analog inputs, and we have 10 of those. So we'll have something like that as well. So that's going to be our analog inputs. And the next one after that, you're going to have floating point inputs, and there are 20 floating point inputs as well as counters. Right. So you're going to have floating point inputs. And because we have 20 floating point inputs, a single floating point input takes 2 integer registers. So 20 of them are actually going to occupy 40 integer registers in our database. And counters will have the same effect, where if you have 10 counters, they're actually going to occupy the space of 20 integer registers. Right? So you have something like this, and you have your floating point inputs. And then you have your counters. So these are going to be what we call the running counters. Right? And then immediately after that, according to our configuration, we're going to go into the binary inputs, the analog inputs, and the binary outputs, analog outputs, and the floating point outputs. So you're going to have binary outputs, analog outputs, and floating point outputs immediately after that. Right. Now for DNP, whenever we see input or output at the server side, we're always saying it with reference to the client. So a binary input will actually be information that is going in input, that is an input to the client, because we always say it in reference to the client. And a binary output is always, as I mentioned, in reference to the client. Right. I'm a little bit OCD, so I'm going to have to change this again to the right color.
Only a little bit.
All right. Like that. So now you're going to notice that with this setup, it's going to be vastly different from our backplane configuration, which I say that's going to be the first problem that you're going to have. So if you see here, we're actually reading from 0 to 100, which means we have that mismatch setup that I was talking about. We were actually reading in that part, and we are writing in the other part. Yeah. So what we're going to need to do is we're going to have to flip these over. Take that one and put it at the top, and then we're going to need to take this one and put it at the bottom. All right. So the first thing that we're going to need to do is we're going to need to change where our read blocks are and where our write blocks are. And then the second thing that we're going to need to change is going to be our read count, our data count. Because if you look at this configuration that we have here, right, we have 10 integers that are working as input. So there's going to be 0 to 9. You have an additional 10 analog inputs, so that will get us to 29. 40 registers that are going to be occupied by our analog inputs, so that's 69. And then 20 registers for counters, which is going to bring us to 89. So that means we're actually pulling some of our output data and sending it to the PLC instead of the other way around. Right. So we're also going to need to adjust that. So first, let's make some changes to this one. Right. We're going to increase our binary data, make that 30 inputs. We'll leave that as well. We can change this one to 30. All right. So this is just going to be the number of binary inputs that you're going to have, the number of analog outputs that you're going to have, the number of floating point inputs and stuff like that. So the other stuff in the configuration, you have the internal slave ID, which is going to be the slave ID for your server. Right? You can put this to anything. This is going to be use IP list, which is basically the whitelist for IP addresses. So you have a part where you can configure what IPs you want to have access to your server, and then only those IPs are allowed to access the data. Right. We are going to disable this because we want it to be accessed by any IP address. Use strip close single point. Now what this allows is for a digital output latch whenever you send an ARM operate condition. Right. We're not going to be using that for now, because it's just going to be a basic illustration. Then what you're going to have, the next thing is going to be, the next thing that we want to talk about are classes. Right. I mentioned before that when you communicate on DMP, you have the option to send data from the server to the client as a group, or what we call a class. Right. So you can classify your data and say, all right, my binary inputs, because as I mentioned, it's only going to be one-sided. There's only going to be information out of your server into the client. So it's going to be an input from the client's point of view, right? So you can make a class for binary inputs. You can make a class for analog inputs. You can make a class for floating point inputs, or you can combine a bunch of data into a single class, right? So in this case, for the rough configuration, default configuration, we have binary inputs in class 2, analog inputs in class 3, floating point in class 3 as well. You have an analog input deadband. Right? Now this one is used when you're performing unsolicited messages from your server to your client. So say you have a bunch of analog input points. If ever there is a value that changes more than 1, that means the previous reading and the next reading, the difference is 1, it will send the value as an unsolicited message. If the deadband was going to be 1,000, that would mean I'll need a change between the last one and the next value to be 1,000. Now, what I need to stress out about deadband is that deadband is not cumulative. It's not like if the value was, for example, if the value starts at 100 and then goes to 200, 300, 400, 500. If my deadband is 1,000, even if the last unsolicited message was when the value turned from 0 to 1,000, if it changes from 1,000 to 1,000.5 and then 2,000, that's 1,000 change from the last unsol, I'm still not going to send an unsolicited message because previously it was 1,500 and the difference now is 500 and not 1,000. I don't know if that makes sense.
Yeah, so that's applied to all analog inputs, is that correct?
To any unsolicited message that goes from the server to the client. So analog inputs is just an example, but for example, floating point would have the same thing. If you had counters, if you have counters on a different server, of course you won't have it for this particular server. But if you have counters that are available for unsols on a different server, you would still get the same thing. The only parameter that would send an unsolicited message every time it changes is a binary change. Because a binary can only change from a 0 to a 1 in the reverse. Right? So every time that happens, that would definitely send an unsolicited message, as long as they've configured for unsols to be sent from your server to the client. So for now, we're going to put the deadband to 1. I mean, I won't be demonstrating unsols, but we won't have enough time for that. Then you have select time operate, which is the delay between when you send a select command, the delay between the select and the operate for the server to operate the digital control once you send a select command. So if I send a select command, before I operate, I'm going to wait 2 seconds. And if I don't get an operate command within the 2 seconds, I'm going to disregard the select command. That is basically what that means. You have the write interval, which is how?
Just can I quickly just go back to that analog deadband?
Yes.
So that, well, I think what Shane was asking is that analog deadband, that's for the whole range of analogs. Like you can't set a deadband for each analog point.
Well, I'm going to go into that a little bit in a little bit.
Oh, okay. Sorry, man.
All right. All right. I apologize for the phone. Just give me 1 minute. Right. So the next part is going to be where will be? All right. App layer confirmation timeout. All right. Which is going to be the timeout when we send a confirmation request on the application layer. So with the nature of DMP, you're going to have communication. The reason why a lot of people like DMP is that it allows you for specific latency on your application layer, on the application layer over the network layer. You see, its reliance to the data link and the independence between the data link and the application layer makes DMP attractive for situations when you have low latency, when you have very high latency, I mean. So our application layer confirmation timeout is a generous value that allows you to disregard the message if you don't have a confirmation on the application layer within a given number of time. Right. Then you have unsolicited responses, which are basically going to be unsolicited messages sent from the server to the client. So this is, do you want to generate or not? Right. And for now, we're not going to be generating that. You have class unsolicited response minimum. Now, what this represents is the minimum number of unsolicited messages that have to be triggered before it sends a class message. So, for example, if I have 10 binaries in my class 1, it will only send an unsolicited message if one of 2 conditions are true. If I have violated the unsolicited message delay, or if I've had 10 unsolicited messages from a given set of class points, right? So for all my binary points, if one binary point changes, right, I won't send an unsolicited message until another 9 binary points change, or that binary point changes 9 times. Or I will send it immediately if 5 seconds pass between the time when the binary changes and if 5 seconds pass since the time the binary point changes. Right? So that means if my binary point is going to change only once, and I still don't get 9 changes within my class, I'm going to wait 5 seconds, and I'm going to send the binary point as an unsolicited message to the client. Then you have the master address, which is going to be the address of the client who you'll be sending unsolicited messages to. Analog events with time. This is just going to be, are you going to timestamp or not? Are you going to set a flag with your analog input data? Are you going to set a flag with your binary input data? Are you going to timestamp your binary events or not? Binary outputs, do you require a flag? Counters, do you require a flag? Frozen point counters, do you require a flag? Are you going to time sync every time before an event is generated? So before you send a class 1 or a class 3 or a class 2 unsolicited response, which is an event for DMP, are we going to sync our time with the client? Then you have the socket timeout. Right. So that's the basic server configuration that you're going to be looking at for DMP. Right. Going back to what we're doing, we set our binary inputs, analog inputs, floating point inputs, our counters, and all that. Right. So now what we're going to have is we're going to have 30 integers as binary inputs, 10 integers as analog inputs, 20 as floating point, and 10 as counters. And this is going to take us from address 0 to address 99. And then at the other side, we're going to go from address 100, we're going to have 30 binary outputs, 10 analog outputs, 20 floating point outputs, and that's going to take us from address 100 to address 159. Right. So we're going to need to go back here, and then we're going to need to change this, because we know we're actually reading from address 100, and we're actually writing to address 0. Right. And does that make sense? So once you make this change, you're actually going to have that flow of information now from this side to that side, and this side to that side. So our read data, which is going to be our DMP output, starts from 100 and stretches on to 159, and that's going to go to our PLC. And what we're writing from our PLC, which is on our write start, we write start from 0, and then we go up to 100 of those. Right. So we're going to have our write start 0, and then we're going to have 100 of those. And our read start, we restart from 100, and then we can just put 100 of count just for uniformity. But we're actually going to have our data in first 60 registers from register 100. All right. Now moving on to the part where we said you have class and you have class responses and you have deadbands. Right. Now, like I said, for DMP, right, when we look at binary, every time you have a binary change, you're going to have an unsolicited message sent. So what the configuration allows you to do, if you double click on binary inputs, right, it allows you to bypass the server configuration for specific binary points. So I can take a specific set of points and then I can put it on its own specific binary class, so that every time when that one changes, I bypass the server configuration and I send based on certain stuff that I've configured for that specific class. Right. I can also group multiple data types in a single class, so I can have binary inputs, analog inputs, floating point inputs, all in one class. So I can take specific points and I can use those points and make up a specific class. So when you asked about having independent deadband values for independent analog points, you also have the option to do that, where you can configure a specific point and say, all right, for point 5, I'm going to put it in class 1 and I want it to have a deadband value of 5. Then you can say point 7 keep it in class 1, but I want it to have a deadband value of, say, 100. Right. So that's going to mean that this one will be subject to the deadband of 5 and will overwrite the server configuration deadband. And this specific point will be subject to a deadband of 100, and this will override the server configuration. Right. I just want to make sure that they're all in the same class. So let me put this to class 3. And then I'm also going to change this one to class 3 as well. You also have the same thing for floating points, where you can set a specific deadband to a specific floating point. And this part is where you configure your Ethernet IP addresses to say, these are the specific clients who are allowed to access my server. So this is where you set the client, the IP list. Right? And this will only be used if this is configured to yes. If this is no, then that won't be used, right, which is the current setup that we have. Then the last part of the configuration is going to be setting the IP address of your DMP server. And you need to set the gateway as well. And once you've done this, you've finished the configuration of your module into PCB. We're not going to download this yet. Right. So what you're going to have is, what do we have? What have we done? We've set our backplane configuration. So we've set the read and write locations out of the internal database. We have also set our server configuration, and we've made sure that we have a flow of communication from the DMP side to your PLC side. So we've made sure that we have a steady flow from one side to the other. We have a straight line that goes from the PLC to this side. And we also have a straight line that goes from our DMP side to our PLC. So now the next part that you're going to need to do is we're going to need to, let's just double check that. We've done this and we've done this. Now you want to change your ACD file to match the PCB configuration before we download it. Now the reason why I say that is, let me show you that, because actually that we're looking at the same thing. All right, so when you get our ACD file, we will send it as a version 12 ACD file that you can open and upgrade in your Studio 5000. And once you upgrade it, you have something that looks like this. Let's just give Studio 5000 a minute, and yeah, there we go. All right, so what you're going to have is an ACD sample file that looks something like this.
Simon, could you restore that down too, please? Make it a bit smaller for us.
Sorry. Yeah.
Yeah, it's good.
All right. So what you're going to have is something that looks like this. All right. So unfortunately, when we deploy it, we would have already have a controller configured for you. We'll have the module configured for you. All right. But it is easy to add in a module if you already have an existing program. And then all you have to do is copy these routines and incorporate them into your already pre-existing logic. All right. So when you download the sample ACD file, as I was saying, it looks something like this. So you have all that logic put in for you, for data and whatnot. You also have a set of controller tags. So you have the controller tags, of course, for the module. And then you have our pre-named DMP card tags, which we try to put in a logical way so that it's easy for the customer to understand. Right. So the first thing that you're going to need to do when you download this is what you're going to have is you're going to have a PCB configuration that is essentially different from the sample ACD file that you're going to have. Because for everyone, no one uses the exact same number of points for binary or for analog or for float or whatnot, and no one uses the exact same configuration. But the sample has to be something standard for everyone. So the first thing you're going to need to do is you're going to need to change this to suit your own sample. Right? So what are you going to have in your routines? You have the first routine, which is just a bookkeeping, a housekeeping routine. So it's the one that transfers blocks, block sizes, and stuff like that. You won't have to worry about this part. The one that you need to worry about is the DMP data, right? Because now the configuration is based on this sample configuration. So it has a read start from 100. It is a read count of 120. The same thing there. You have a block transfer size of 60. Right? It also assumes that you have 20 binary inputs, 40 analog inputs, 20 floating point inputs, and so on, which is vastly different from our configuration. Right? So the first thing that you want to do is you want to change the values in these tags to match with your configuration. Right? For example, we have the number of DMP binary outputs. We are using 30. Right? So you'll find in your ACD sample, this will be different from 30, and you want to set this to the one that you have. And you want to do the same thing for your analog outputs, where we have 10 of those. For your floating point outputs, oh, how many of those do we have? Floating point outputs, we have 20 of those. You want to set that there, right? And you also notice that when you change this, you're also going to need to change the starting registers for all the other parts, right? So for here, if I put 30, then that's going to be reading from 0 to 29. So it means my next copy is going to be from 30, from read data 30, array number 30, and then you're going to copy 10 of those, so that's going to be 30 to 39. The next one would have to start at 40, and that's going to be 40 to 80. Right. This is for our binary output. For our binary input, we are going to need to do the same thing. So 0 will be stored at right, and we'll go 30 of those. Right? And analog input would also be stored from where we left off, from the analog out, from the binary output, which is at point number 30, and then 20 of those, 40, and these have to be 20. Because, okay, all right, I made a small error there. All right, so we're going to have our read data. All right, let's just cross-reference that. We want to go into our tags. I want to see what data type we're using there. All right. All right, so we're going to need to copy 40 of those because we're copying integers into that. And then we are going to have to copy 40 of these because we're copying floating points into integers. All right, like that. Then we have our control registers. And we actually have 20 of 10 of these. All right. So the next part, as I mentioned, you're going to need to change your ACD configuration to suit that. Once you've done that, everything else is basically the same. You don't need to change anything after that. What else are you going to see? Just walking through some of the tags that you have in your DNPSNET, you have status tags, which are going to hold the status information of the module. I'm going to explain those once we download and we go online. You're going to have data tags that are going to store your data. You have command control bits as for warm boot, cold boot, get time, set binary events, set analog events, things like that. And then you're going to have tags that are going to hold your clock data, your binary events, your analog events. So you can actually create an analog event out of your logic from your PLC. Not only relying on unsolved messages, you can create an event if a certain condition is met. So say the chlorine goes over a certain value, and at the same time the methane is also going over a certain value. You can incorporate all that data and create a new event that you're going to send to your client that is independent of the ANSO configuration or the PCB configuration that we put in the module. All right. So once you've done that and you've configured that, you've merged your ACD file to the PCB configuration that we've made up. The next stage is we're going to need to download the file to our PLC before we download the PCB configuration to our module. Right. So for this one, you go online with your controller, you set your path and whatnot. Give logic 5,000 minutes. All right, then you can download that. You can set it to run mode. Before you download to PCB, you have to make sure that the logic is in run mode in your controller. All right. So some things that I want to show you before we continue to download the configuration to our PCB file is parts of the status, right? So the four most important stuff that you're going to find in your status are going to be your scan count, your read count, your write count, and your pass count. Right. So your scan count is going to be the number of scans that are going to be occurring between your PLC and your controller back and forth, right? So you're going to have a value that is constantly changing in this manner. The same with your read count, which is going to be counting the number of read blocks that you have, and your write count, which is counting the number of write blocks that you do. And your pass count is going to be basically counting the number of exchanges, read and write. Right. So a good way to see if the module is working, if the module is running properly, is if you have constantly changing values. This will automatically tell me that my module is working on the backplane without any problems. Right. So once you have that part set up, we have this running, the next thing that we want to do is we want to download our PCB configuration to our module, and that is done through the serial configuration port. You download. And then because it's serial configuration, it's going to take a bit of time, so we're going to let that do its thing. So once you do that, you download your ACD file. You change the configuration to match your PCB. You download your ACD file. You download your PCB file as well. Then you can basically just relax and have a beer. I mean, you might need to test first just to make sure that everything is working, but that is basically the end of the configuration. So I'm just going to walk you guys through doing some diagnostics, and then we're actually going to see if the whole thing is working. So we're actually going to test it out. And we are going to take a look at the diagnostic window, and then we're going to take a look at the communication. All right. So let's go back to that one. Share screen. All right. From here, we want to go to our diagnostics window. All right. So unfortunately, the old modules used to have an old serial diagnostic method, which is a bit cumbersome, but it's actually still just simple. So let me just check my serial port. Just need to check something just to be sure.
Making more sense, right?
All right. So there we go to diagnostics.
The older software that we were using back then wasn't user friendly.
All right. So from the diagnostic window, what I want to show you guys, the first thing is going to be the database view. Is that, and it's going to show us the information that is within our database, right? From all the individual database addresses, particularly we're working with addresses 0 to 99 as well as 100 to 199, right? And from our configuration, we set our read stats to 100, our write stat, which is going to be our analog inputs, binary inputs and stuff like that, from 100 to 60, from 0 to 60, right? So if we go to our controller tags, we want to minimize that. We want to go to our data, binary data. We're going to put some test values there so that we can see are we actually getting that stuff at the other side. All right. All right, there's a small thing that I forgot to mention to you guys. A small error that we have here that I'm going to show you later. Or let me just show you the effect of the error, right? You'll notice that here we have our binary inputs going from 0 to 19, but we actually need 30 of those. So we're actually going to have to change our data type, our data array to a larger value, which we'll do later. But I want to show you guys the effect of having a small value there. All right. So let's put some analog values, 1.1, 2.2, 2.3, 4.4, 5.5, 6.6. And if we go to our diagnostics window and we look at our database where we're writing, you see the values that we put in, right? Our binary values and our floating point values in their 32-bit format. Now, what I wanted to show you guys is, I mentioned that we are polling 30 binary inputs, but we only have space for 20 of them. So that is going to create this problem, where you have these analog output values repeated on top in your internal database. Because when it tries to copy those 30 values, as I mentioned, the binary and the analog are going to be back to back. So when it copies 30, it's going to copy all 20 of our available binary bits, and then it's going to go to the next one and then copy 10 of those. Right? So this can easily be fixed by increasing the data size under your user-defined tags. Right? So user-defined tags, you're going to have binary tags. You have your binary inputs. You want to change this array size to 30 instead of 40. Now I cannot do this, or let's just do it now. Go offline, then we change this one to 30. Our binary input is large enough, so we're going to leave that the way that it is. We're going to apply that. Yes. Then we go back to our controller tags. Now we have enough tags to cover that. Once you do that communication, we're going to download that. Yes, we're going to switch it back to run mode. We're going to put some binary inputs there. And then we're going to put some analog inputs there. Let's put some floating point inputs as well. All right. And then if we go back to our diagnostic window now, pull that 0, now we have our data set in the proper way that it's supposed to be. So we have 30 binary inputs going in first, we have 10 analogs, then we have our floating points, then we have our counters and whatnot. Right. But this is only one side. So this is communication between our control logics and our DMP cards. Now to demonstrate the whole part, I'm going to need to use a simulating software for DMP. Now we use protocol test harness. Let me minimize that. Unfortunately, we're going to have like a large number of screens open just to make a demonstration of this. All right, so I'm not going to walk you guys through the setup of protocol of test harness. That will take us another 30 minutes just to set up. So I'm just going to open a control workspace that I already made, that I pre-made before this. All right, it has everything set up. And what we're going to look at is we're going to open our data window of protocol control harness. So it's going to show us the data in all our DMP points configured at the master, at the device. Right. So if you notice, our analog inputs are coming in. All right. Let's change some of these values and see if that actually changes, if we actually have communication, or if these are just some preset values that Simon put in to try and fool us and show us that the system is working when it really isn't. All right, we go back to our data window in our protocol harness, and we can see that real-time information coming in. So we actually have data being transversed between our DMP device, this is our DMP client, and our PLC. Right? Now let's try those analog outputs now. The problem with protocol test harness, it makes it a little bit complicated to, it's not as user-friendly as I would like myself. So no, we want analog output blocks, and we want to write certain values. So let's go to address 0. I want you to notice this is going to be the data block where we're going to be writing the values that we're going to be putting in. So we write that once, we go to 1, we can write that again, we go to 2, 3, let's put a different value now, say let's put 5, 4, point number 5, all right. Let's change stuff a little bit. Oh, okay. All right. So you notice that we've put values in our analog output, right? And what we're going to expect is we're going to expect to see these values in our diagnostic window, right? But we're going to need to see them from address 100 going forward. And these are the values that we just put in, right? And these values are going to be sent from this guy for a controller. So we want to look in the controller and we want to go to our analog outputs and we are going to see these values. All right. So those values are going to be coming in so you can have full communication from one side to the other side. All right. I'd estimated that this was going to be an hour's session, but it seems to have run 10 minutes over. I may have underestimated how long it would take. I don't know, do you guys have any questions? So this is basically the full setup for configuring your DMP to communicate.
Yeah, look, Simon, I think you've covered most of it. I think the guys have picked up where they've had their issues, so I think it's covered off the as to what they need to do to configure it. So thanks for that.
That's okay. I'm going to, as I mentioned, I was recording this, so I'm going to save it and then I'm going to put it up on YouTube for you guys to